Hello. So in this section, we'll be looking at now solving equations with trigonometry. So equations with sine, cos, and tan in it, right? And in this section, we'll be focusing on equations that look like, say, sine x is a half, or cos x is minus root 2 over 2, or tan x is 1, right? So essentially we want to find the angles x such that if we plug that into the equation, it satisfies it. And basically we will be looking at many different types of trig equations throughout this course in this chapter and in year 13, right? But no matter how complicated the trig equations we will look at, and we will build upon this, it all boils down to basically solving sine x equals a number, cos x equals a number, or tan x equals a number, right? We want to eventually we will reduce equations to one of these three sort of equations, right? And that's what we're going to be looking at. This video will be a building block or a foundation of solving trig equations, which will be important for later chapters. So this will be very, very important video. I'm going to try and start simple then. Before we look at proper examples, I'm going to sort of cover the different types of solving we'll be doing to cover all bases, right? So I'm going to try to do fairly simple examples here. Let's start off then. So first of all, we might get, say, an equation like sine x is a half, right? Now, what we want to do is, first of all, obviously, if we did the obviously from GCSE, you'd do inverse sine, right? And that's what we're going to do. So if we do inverse sine of this, that will get me 30 degrees, right? Now, that is one solution, right? That would be one solution. X would be 30. But in actuality, there'd be more solutions. Let's have a look. So the common strategy will be then is to draw the sine graph, right? So say we have 360 here. We're going to consider the sine graph then, right? Now, we want to solve sine x is a half, which means obviously the top up here is 1, so a half would be there, right? And then if we read off our graph here, there we are. There are two solutions, right, which is where it crosses the curve, there and there. Now, the calculator will always give you the closest solution to 0. In other words, it'd be this solution here. That's telling me this is 30, then, right? But we have seen there's another solution here, right? Now, how are we going to find that solution? It's going to be to do with the symmetry of the graph. Now, how are we going to find that then? Well, what we're going to do, we're going to look at the gap between this end of the left part of the curve. So starting at 0, then to the first solution at 30, the gap will indeed be 30 then, right? Right, between 0 and that solution 30 will be 30, that distance. In the same way then, from this other solution, this other point, the gap between that point and the other end of the curve, we should be at 180 here, there, when it goes back to 0. That gap between 180 and this other solution for x here would also be 30. Which means then if the gap or the difference between the solution and 180 is 30, the other solution would be 180 take away 30. Okay, and that'll be 150 then. And so that idea then of considering the gaps at either end is what we'll always want to do then, right? By the symmetry. Now the other possibility is, what if we have a negative? So say sine x is now negative a half instead. So it's a slightly different way of doing things. Again, if we do our calculator and put in inverse sine of minus a half, we would get minus 30 degrees, right? So that could be then one solution, right? Minus 30. Now, again, we're going to then consider the sine graph to help visualise. Say again between 0 and 360 degrees, right? Right, so if we have negative 30 then, because we have a negative angle here, we need to consider like the negative part of the graph. So let's go a bit that way. Right, so then negative 30 would then be about there, say. So then if we then, read off the graph in this case, we would get two solutions over here, right, on the other side of the graph. How are we going to get those then? Well, this first solution, the next solution, that's the next solution after minus 30, that solution there. What we're going to do then is, again, consider symmetry. So the symmetry then between the minus 30 here and at 0, right? Between minus 30 and at 0, right? That'd be a gap of 30, right? Between minus 30 and 0, right? Those 2 points. The gap between there will be 30. Now that is the same gap between here is 180 and this next solution there, right? Again, if we read off, that's that solution there. The gap between 180 and the next solution would also be 30. It's symmetrical, right? And that's what we'll be using, right? So to get the next solution after minus 30, well, because it's 30 away, because it's the next solution is 30 away from 180, we need to add 30 to 180. So all we're going to get x is 180 add the 30 then, right? Hopefully you can spot that again, because the gap here is 30 between 180 and the solution. Same as the gap between minus 30 and 0, right? Anyway, if we do that, then that'd be 210, which tells me then that this solution is 210, okay? Now, as for this next solution then, if I read across that point there, right? There. To deduce that solution, well, we're going to recall that the trig graphs repeat themselves. So in the case of the sine graph, it repeats every 360. So if I say draw the graph again, so we have 360, right? And then we can go backwards. There we are. And if we then do that, that'd be minus 360. So the graph repeats itself, 360, means it returns back to where it started, right? So if we have minus 360, say there, then at 0 here, that is where the graph starts to repeat itself, and the shape, and you can see the shape repeats, right? The shape of the graph. And then 360 is there, and then if we were to draw that graph afterwards, I had to shrink it a little bit, but the graph repeats itself again, right? And you can see that there. Now what that means is that every 360 degrees, the point reoccurs. What I mean by that is, if we have the point here then, say, this would be minus 270. That same point would then be on there, right? But 360 along. Hopefully that makes sense. And that point would be 90. So we can see here that minus 270, if we add 360 along, that would then get us 90. Well, there we are. So we get the same point again after 360 degrees. Which means, because the graph repeats itself every 360 degrees and the graph goes on and on and on, we can keep adding adding or taking away 360 and get the same sort of point, right? And we can use that to solve. We can use that to find other solutions. Okay, so if I get rid of this, then hopefully get the idea then that the graph repeats itself and the points repeat as well. Wow, this hopefully this you see here. This point at minus 30 would be the same point here, which is 360 along from this point at minus 30. That's the same point on the graph, right? The graph repeats itself at minus 30 and at this point there. Which means, to find this third point then, we can add 360 to minus 30. So, we'll either have then, x is minus 30, add another 360. If I do that, I get 330 degrees. And that would be the other solution there. So, once we found the first two solutions, essentially what that means is I can keep adding 360 to my two solutions to get more solutions. So my I'd say like my main two solutions, right? X is minus 30 or 210. But then to get more solutions after that, I can just add 360 to each number. So minus 30 add 360 with 330. 210 add 360 would be 570, right? And 330 then, so now I'm adding 360 to 330. I then get 690. And if I did the same then to 570, I get 930. And it keeps going on and on, right? Because obviously the sine graph would keep going on and on as well. So there are multiple infinite solutions by just adding 360 to the first two solutions I get, okay? Now, the first two solutions I get from looking at the sine graph, then I can just keep adding 360. I could even take away 360. So if I went the other way around, if I had, so if I did minus 30 there, if I did 200, if I did 210, say, so my two main solutions were minus 30 and 210. If I then did 210 firstly, take away 360, I'd then get minus 150. And then if I did minus 30 minus 360, I would get minus 390. And then I can just keep minusing 360 away, right, from all of this. So minus 150, take away minus 360, I get minus 510. And I can do the same there, minus 390 minus 360 will be minus 750. And again, I'll keep getting more solutions by subtracting 360 as well from my numbers that I've got. So, the point here is, once I've found two solutions, I can then add or take away 360 to get other solutions, right? But yeah, so these are the solutions we can spot in this case, okay? Right, so that's like the sine, that's like equations with sine. Those are sort of like the two sort of cases, right? If sine is negative or sine is positive, that's sort of the two ways we solve it, right? Now, let's do the same for cos. So now we have, say, cos x is a half. So again, if we do inverse cos firstly, we get 60 degrees. So my first solution would be 60. To find the other solution, we then can consider the graph, right? Say between 360 there. Now, so we know one solution is 60, which should be about there, right? Say. So then the other solution would be somewhere there, right? Another solution x. To find that one in this case, if we consider the symmetry, well, in the middle of the curve, right, at the bottom there, it means the left side is the same as the right side. It's symmetrical. Okay, hopefully you can see that. That means that, the gap then between 0 and 60, the first solution 60, is indeed 60 then, right? That is the same gap then, or the distance between the second solution of x and 360, the other end of the curve. So that gap will also be 60 because of the symmetry in the middle, okay? Now, what that means is then, the other solution then is going to be 360 take away 60 to get to that point x there, okay? which should be 300. And there we are. So we found the two solutions and the two solutions close to each other. To find more solutions, right, if we were to continue the graph on, like as so, we'd get two more solutions there. If we were to find more solutions, we just need to add 360 to these two numbers, right? So then we would have, or x would be 60 add 360, which would be 420. 300 add 360, that'd be 660. 420 add 360 would be 780. And then so on, right? We'll keep adding 360 to every number in this list to get more solutions. We could also take them away. So if we did 300 firstly, take away 360, we would get minus 60. And then if we did 60 take away 360, we'd get minus 300. And then minus 60 minus 360 would be minus 420. And again, we can just take away 360 as well. Okay, so I make a note of add 360 here and take away 360 there. So once we found the two solutions next to each other, so 60, and then the next solution after that is, well, it'd be 300 here. Once we found the two close solutions, we can then find other ones by adding or taking away 360 to those. Okay. Right, so that's when cos is positive. What about if cos is negative? Say we had cos x is minus a half instead. Again, the first step is to do inverse cos of minus a half. That would be minus 60, I believe. No, 120, sorry. Oh, 120. Okay. Right, okay, so you get that from the calculator then. So the first solution could be 120. So then to find the other solution, let's consider the cos graph. Again, between 360. So the first solution is 120. That's going to be there somewhere, right? Now again, in the middle of the curve, at the bottom, it's symmetrical either side. So we're going to apply the exact same idea. So at the start of the curve, at 0 here, the gap between 0 and the first solution, 120, is 120. So then the gap then between the next solution, which should be there, right, that's solution x, and 360 at the other end, that gap then, that gap between x and 360 will also be 120 then, right? Which means if you want to get the next solution after 120, this point here, I need to take away 120 from 360. So then I get 360 take away 120, which would get me 240, right? And those are my two sort of primary solutions, if you will. To find the other solutions after that, we can just add or take away 360 to these two numbers. So we could either then get x could be, well, 120, add 360. That would be 480. 240, add 360. That would be 600. And then we just keep adding 360s onto this. So 480 then, add 360. Gets me 840, and then so on, right, by adding 360 to every number from there. Okay, or you could even have by subtracting 360 instead. The other solutions, so 240 take away 360 is going to be minus 120, and then 120 take away 360 would be minus 240. And then if we did minus 120 take away another 360, that would get me minus 480. And so on, right? And then this time I'm subtracting 360. So I can get other solutions by adding or taking away 360 to these two numbers here. Okay? So that will always be the step then if cos is negative. If we negative a half in this instance, we can find the two solutions this way and then add 360 or take away 360. So that will be the idea about the gaps at either end of the curve, right, between 0 and the first solution and the second solution and 360 at the other end, that sort of gap has to be equal, right? This gap there and there. Right, okay, so that's cos then. Lastly, we got tan. And actually tan's easier than the other two. So say, for example, if we had tan x is 1, so first of all, positive tan. So if we then, well, if we do inverse tan, right? Inverse tan of 1 gets me 45 degrees. So that's the first solution, right? X is 45. So then if we consider the tan graph, it looks like this. 90 here. 270. And there we are. 360 there. Now, 45 would be about there, right? Okay. So the other solution then, if we read off in this way, it would be there. How do we get to that point? Well, that's the point. Now, you should know the tan graph repeats itself every 180 degrees, right? Unlike the sine and cos graph, it repeats at 360. The tan graph repeats every 180. So to get this next solution and hopefully spot that this point here at 45 is the same point here, right? Because the point's repeated at that point. So you just need to add 180 on, right? It's the same point on the curve essentially. So we need to add 180 on because that's when the graph repeats itself. So the other solution would be 45 add 180. Okay, which would be 225. Okay, and the reason why I said tan is easier is because there's no sort of symmetry you need to pay attention to. The only solution you'll get is from the calculator. Then you just need to add or take away 180. So if we had x is 45, then the other solutions would be if we add 180 to this, well, we got 225, right? Then if we did 225, add another 180, we'd get 405. Oh, sorry, 405. If we added another 180 on, I get 585, and so on. And so therefore I can generate more values by adding 180 to my initial value, right, of 45 from the calculator. And again, we can go backwards. We can subtract 180 from 45. So then I could either get 45 take away 180, which would be minus 135. And then that take away 180 would be minus 315. And then so on, right? And that is when I'm taking away 180 degrees. So those are the solutions I would get in that case, right? But there we are. Right, the last possibility, of course, is if tan is a negative value. So, for example, tan x is minus 1 instead, right? So again, if I do the inverse tan of that in my calculator, I get minus 45 degrees. Right. Now, again, we're going to consider the tan graph. So 90 there. 270 there for the asymptotes, and then we're back at 360 there. So minus 45, so that's a negative angle. So if I just draw this graph on a little bit more backwards, so the asymptote would be at minus 90 there. So minus 45 would be about there, right? Oh, let me draw it a bit better. That would be where minus 45 would be, roughly, right? Somewhere there. If we then extended that on in this way, to spot the other solutions would be there and there, where it crosses the curve. How are we going to find those? Well, the only way, once we found the first solution, which is minus 45, again, hopefully you notice that point at minus 45, and this point here, and that point there, they're all on the same point of the curve. So you just need to add 180 on, because that's when it repeats. The tan graph repeats 180. So we just need to add 180 on to this value here. So we're going to get, or x is going to be minus 45, add 180, which would get me 135 degrees, and that would be corresponding to that point there. And then to get this other next point, well, we need to add another 180 on. So then that'd be 135, add 180, which would be 315 degrees there. And there we are. And so there we are. And so the general gist with the tan graph is what again, it's simpler because we can use the calculator to get one value like this, and then we just add or take away 180 to get more values. Right, so that is basically, I guess, all the different types of equations when we're solving. That's hopefully the examples are helpful to be able to read off the graph, essentially, right? This is all the examples we'll look at when we get a trig equation. One of these sort of 6 sort of cases or examples. This is what you need to do, right? So every example we'll look at will basically boil down to one of these 6 cases. So hopefully you kind of understand how we use the graphs here to first of all look at the symmetry, to find the 2 solutions, and then we can find more solutions because by adding 360 or taking or 180 or taking it away, right? Because the graphs repeat themselves, okay? But that's the idea then. So we're going to look at and the last thing to note, I should say as well. Now the answer, the number we get from the calculator, or the value we get from the calculator, or the solution from the calculator, that initial solution, right? We call that the principal value. So that's just some terminology to be aware of, or the principal solution. Okay, so principal, meaning like the first or like the main solution there. But yeah, so that's being able to solve all the various types of equations we'll be looking at, and at the most basic level, right? Hopefully these basic, I tried to be sort of simple as possible. Hopefully these have helped to be able to look at the graphs. But basically all trig equations should boil down to like these sort of 6 examples there. So hopefully try and wrap your head around that. Hopefully it makes sense. But let's look at some proper examples now. Right, so let's start looking at some examples then. So we firstly need to find the solutions to the equation sine theta is a half between 0 and 360, right? So again, we can do inverse sine firstly. So we did inverse sine of a half, we would get 30 degrees. So that means one solution could be 30. Remember, that's the principal solution, the one you get from the calculator, the first one. So to find the others then, let's consider the sine graph. So between 360. Right. So then 30 would be there. So then this next solution, well, again, the gap between either end of this curve, right, is going to be the same. Well, the gap between 0 and 30 is 30. And so the gap here between this next solution for theta and this at 180, when the curve goes back to 0, that gap again is 30 between the second solution and 180. So then to find the other solution then, we're going to do 180 take away 30, which should then be 150, right? Now, that's it, right? To find the other solutions, we would have to continue the curve on, right? And then add 360 on, or take away if we were to go backwards. But actually, those are the only 2 values of the curve between 0 and 360. So there we are, right? So therefore, that's it, right? So that's my solutions, 30 or 150 between 0 and 360. right? Because adding 3, because that's it, right? Those are the only two solutions. Right, okay. Now I'm going to show a different method then. So I'm going to call this one method 1. And I'm going to call it the graph method, right? I will be working with this method later in other videos. I think this is the better one, the main one I find. But we can use the cast diagram as well, which we looked at earlier on in the chapter 2. So the idea is with the cast diagram, well, we don't need to consider the sine graph, but so we're going to start with sine theta is a half. So then obviously we do inverse sine to get that first solution. That would be obviously the first thing you do. You get 30. Right? Okay. So then, remember when we drew, we have our full quadrant grid. So we want to mark 30 degrees. Remember, we always measure the angle anti-clockwise from the positive x-axis, right? This is x. So we go all the way around it that way. And then if we do a full turn, it'd be 360, right? So then 30 would be about there, right? Now, there are 4 other possibilities. Remember, we measure the angles from the x-axis. The other one could be there. The other one could be there. Oh. The other one could be there. That could be 30. Or we could have another one there at 30. So there are 4 other possibilities. But remember, this second solution in the second quadrant, well, actually, that would correspond to the angle 150, right? Then the third solution in the third quadrant, that would be 210, right? If we then did all the way around, so there, that'd be 210. And then the final solution there, well, that'd be 330 the way around there until we get to that angle. So which other angles can we get? Well, this is where we label it cast, right? Remember, C-A-S-T in the 4 quadrants. So C stands for cos, S stands for sine, T stands for tan, and A stands for all. So all 3 of them, cos, sine, and tan. So the idea is that each quadrant represents when each of the trig functions are positive, right? Now, in this case, sine theta is positive a half, so it has to be positive. So that means what spaces or what quadrants get me a positive value for sine? Well, A, for all, that means sine has to be positive because that's all the trig functions are positive, right, in this first space. But then also S for sine here. So that means sine is also positive at this angle here in the second quadrant. So then we just need to work out what that angle corresponds to. So then we start from 0. Right, if we get rid of all this. So we start at here and the positive x part, and then we work our way around to get that angle, which should be 150 then, right? Because obviously it'd be on the line over all the angles 180, but we have a 30 there, so we have to take that away to get 150. So that's my other angle then, right? So sine is positive, so therefore theta is 150 as well. So it could be 150 or 30, right? So it could be 30, the first solution, or 150. That's how we can get the other solution using the cast diagram. And then obviously to get more solutions, then we'd have to add 360 or take them away. Alright, these two values, add or take away 360 there. Okay, cool. Right, so we've got this question then. We need to solve in the interval 0, 360 again. 5 sine x is -2. So now obviously we've got a 5 in front of the sine x. We just want sine x on its own. So we're going to divide both sides by 5 to get sine x is -2/5. Now again I'm going to do inverse sine. So if I do inverse sine of -2/5, I get minus 23.578 blah 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 degrees, right? So then if I do the sine graph then to help me, well, if I go between 0 and 360 degrees firstly, it'd be there. But then I have a negative value for x, right? I have a negative angle, so let's consider drawing a bit more. So minus 23 would be about there, right? Minus 23.6, say, right? That's that angle. So then to get this next solution across over here, well, again, if this is 180 then, when it next reaches 0, well, then the gap between this minus 23.6 and 0, which would just be 23.6, right? The gap between there is the same between the gap between 180 and this next solution here, right? Which would, again, the gap has to be 23.6 then. So to get the other solution then, we're going to need to add 23.6 to 180, right? To get the next solution. So it's going to be, or x is going to be 180, add 23.578. And if I do that then, put that in the calculator, I get 203.578 ... degrees, and that'll be there then, right? So this would be 203.6 degrees, right, for the next solution there. Right, so then to get this other solution then, well, notice that's the same as it's this 23.6 repeated, right? Which means I need to add 360 on to this minus 23.578. So the other solution would be x is minus 23.578, add 360, because the graph is repeating at that point, right? Hopefully you can see the 2 points, the 23.6 and this next solution here will be in the exact same position, right? But just 360 along. So if I do that then, I get 336.42 blah 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 degrees, right? So that'd be 336.4, right? And obviously we're at the end at 360 there, right? So actually those are the only two solutions between 0 and 360, right? That solution there, and again this solution there, between 0 and 360 of the graph. So that's it then. So again, so in this interval then, between 0 and 360, the only solutions we have between 0 and 360 is this 203.578, which are around to 6 degrees, and this 336.4 degrees, right, to 1 decimal place. And that's it, right? Obviously this minus 23.578, that's negative, that's outside the range. So also be aware that the calculator won't always give you the first solution to the interval. Okay, the interval you do need to check, but we can use this solution from the calculator to work out all the other values that do lie in the interval to find the solutions we do want. Okay, but there we are. So there we are. Now again, that's one method we can do things by considering the graph, which helps us find the solutions. But we can again use the cast diagram if you prefer. So again, we found the first solution. So we had sine x is minus 2/5. So then we inverse signed to get the angle x to be minus 23.578. Right, so again, we're going to draw that angle then on our 4-quadrant grid. So negative 23.578, the angle's negative. So remember, the positive direction, we go that way. So then we go the opposite way if it's negative. So we measure the angle that way instead. So if we go 23 below, it would be about there, right? So that'd be like 23.6, say. right? Now then, again, between the x-axis, we'll have the other three possible angles. This will be 23.6. We could have that angle from the x-axis at 23.6. And we could have that angle at 23.6 as well. Okay, obviously, forgive me, the measuring is a bit weird. Let me draw that a bit better, actually. There we are. So obviously, when we measure each quadrant, each of the four spaces, if we measure the angle from the x-axis, we get those four possible angles. So which other angle do we accept then? Well, if we label our diagram cast, so our to sine x was negative, right? So I'm going to say sine x is negative because obviously it's negative 2/5. So we want the angles to be in the negative, in the space when sine is negative. So that's where this lettering helps us. So sine x is positive here because s is sine. That's why sine is positive in that space. But also here, a. That means all. So that includes sine, right? So sine is positive there as well. So when sine is negative then, it's going to be these two spaces then, right? Because only cos and tan are positive there. Well, obviously this represents the first angle, minus 23.6. So then to get the other angle then, well, then we go, we measure the angle then, right? So if we get rid of these two then, if we measure that angle, that would be 180 add 23.6, right, degrees. So if we do that then, so the other solution is going to be, or x is 180 add this 23.578. If I do that in a calculator, I get 203.578 blah 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 degrees, which matches this solution we got up here, right? So those are my two solutions then. So then to get the other solutions, I can add 360 to the two solutions I already have. So if I do that then, well, minus 23.578 add 360 here. If I add 360 to that to get the next repeating solution, I get the other angle, 336.42 blah 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 degrees. And then actually, if I added 203, then the next solution, if I added 360 to that, I'd be outside the range, right? Remember, we are only between 0 and 360. So the only values between 0 and 360 here is going to be 203.578 and 336.42. So there we are. To one decimal place, and there we are. So those are my two solutions here, and again that matches with the answer, right, that we got up here, right? Same two solutions. So the two different methods, pick what you prefer. Again, I recommend, and I will be working with the sign graph for later examples, but both methods get you the same answers as long as you know how to use them, right? But there we are. Cool. I should say all here. Okay, so let's move on to another example then. Okay, example 12. Solve in the interval between 0 and 360. Cos x is root 3 over 2. And actually, quite interesting question. We're actually given another piece of working out from someone else. So the student then firstly did inverse cos to get 30. then they deduce x was 30, or 180 take away 30 to 150. And it said identify the error made by the student. Now, I guess with these type of questions where you got to examine some working out, probably it's the best idea to try it yourself, because obviously the question most likely will then say find the answer, right? So you're gonna have to do the working out anyway. So Matt, it's best to kind of like kill two birds with one stone. Instead of trying to analyze word by word or line by line, you just try to do it yourself and then see where your answer starts to diverge or not follow the working out they've done. Anyway, so let's just try and solve it, right? So again, the first procedure will be to do the inverse cos of root 3 over 2. And if I do that, I get 30. Right, so that's right. Okay, that first step's right. But then to solve it, then obviously that x is going to be 30. So then to get the other solutions, let's consider the cos graph. Here. So between 0 and 360, right? There we are. So 30 is going to be, say, there. So then the other solution, where again, the idea then, the gap between 30 and 0 at either end of the curve, so that gap's 30, and this next solution and 360 at the end of the curve has to also be 30, right? The same gap, because it's symmetrical, right? It's symmetrical in the middle of the curve. There we are. So then if we then, the other solution then be 360 take away this 30, which should be 330. Hang on a minute, they did 180 take away 30. So that's the wrong part. So the error made is the student did 180 take away 30 instead of 360 take away 30, right? And that's the error then, right? Which then led to a false solution, hence a false solution of 150 degrees. Okay, and then part B then, well, we've already done part B as well. See, we knocked two birds out with one stone. So then part B, we did our solution already. So therefore, if I do it down here, between 0 and 360, x would either be 30 or 330 degrees, right? These two values there. Those are the only two values, and you can see by the graph, the only two values that are between 0 and 360, there, right? There and there. Cool. Right, okay. Okay. Now we can step this up again, right? And we can also introduce the identities that we looked at in the last section, which you should remember that sine, where should I do it? That sine squared theta and cos squared theta is identical to 1, and tan theta is identical to sine theta over cos theta, right? Remember, you do need to remember those identities, and we can use that to simplify equations, right, to make them solvable. Okay, now, before we do look at the question, I do want to emphasize, and really do emphasize, because I do see it does trip some students out in certain questions, the idea that you need to factorize whenever you can. For example, if we had the equation sine x cos x equals, let's say, cos x, right? Now, some people would be inclined to say, well, actually, we can use this tan identity here. If we then divided both equations by cos x, I get the simpler equation. Well, sine x over cos x. Well, firstly, that just leads to sine x. And then cos x over cos x is 1. Well, actually, we didn't need the tan identity, actually, because the cos is cancelled. But anyway, we get this equation, sin x is 1. Well, then you'd get the solution then. We did this as a sine graph at 1. The only solution would be 90, right? However, the problem is when you need to be so careful, so careful if you're dividing by sine, cos or tan, because you might be missing a solution. This is why I say you need to try and factorise first before you start to resort to dividing by stuff. We can factorise this expression and not lose any solutions, because what we can then say is if we move the cos x, so I'll make a big cross there, so if we move the cos x to the other side first, minus cos x equals 0, well then a cos x is common to both terms, right, of the equation. I can factor a cos x and say sin x minus 1 equals 0. Well, what do you know? Again, we've got two factors, so set them equal to 0, so we either get cos x is 0, or indeed sin x equals 1. Well, that sin x equals 1 matches this. So we get that equation and that solution, right? But we would also we missed out the fact that cos x could equal 0 as well. So we'd need to solve that as well. And so if cos x equals 0, so this is the cos graph, at 0 it would be there and there. That would be 90 and 270. So we'd get 90 but also 270. We missed out the solution 270 from here, right? So that is the incorrect way of solving, by dividing when you instead can factorise, okay? When you cannot factorise and pull out any terms out, then do divide, because you're not missing out a solution. But when you can factorise, you should factorise. Right? Always check if you can factorise first. It's so important, so I'm going to highlight that. I'll highlight that here, right? Now, with that in mind, let's have a look at this equation then. Right, so we have sine theta is equal to root 3 cos theta. Now, try and look at the identity and see what we can do there. And so again, my first tip then, as I said, try and look at factorising. If we then move that root 3 cos x to the other side of the equation and equal 0, well, I cannot, in this case, I can't factorise anything out. The sine x, the sine theta term, and the root and the cos theta term, there's nothing common between them, right? So I can't factorise anything, so I am allowed to divide to make it simpler in this case, right? So what I'm going to divide by, well, I could either divide by sine or cos. Well, this will help me actually, this tan identity. Well, I have sine theta over cos theta. Well, then let's try dividing the equation by cos theta then. So then sine theta over cos theta minus root 3 cos theta over cos theta equals 0. Well, 0 over cos theta is still 0, right? Well then, hopefully you recognise sine theta over cos theta is tan theta. And cos theta over cos theta just 1, because they cancel out. So just tan theta minus root 3 equals 0. Well then, if I move that to the other side, I therefore get that tan theta is root 3, and I can solve that now, right? So then I can look at the tan graph then, right? So firstly, again, I'm going to do inverse tan of root 3. If I do that on the calculator, I get 60 degrees, right? So if I look at the tan graph then to find the other solutions, well, the tan graph looks like this at 90, 270, and then 360 there. So again, between 0 and 360, our interval. Do check the interval, by the way. Sometimes it won't be 0 and 360. But yeah, anyway. So 60 would be about here, say, right? So then to find the other solution there, well, that's when the graph repeats itself again, right? Hopefully you can notice. If I added that part on, the graphs are just 180 away from each other. So I just need to add 180 to get the other solution there, right? So that means x is 60, or 60 add 180 on, because it's repeating, right? If I do that, then I get 240. And actually then, between 0 and 360, 360 at the end there, those are the only two solutions then, right? When tan theta is equal to root 3. So there we are. So I'm going to say between 0 and 360, x is 60, and 240 degrees. So those are the two possible solutions there. Right, okay, so again, I just want to emphasise one more time, we could divide here by cos theta, because I couldn't factor out a cos theta, right? I couldn't factor anything out, so I wouldn't be losing any solutions there, but do try to factorise whenever possible, right? Anyway, okay, so let's have a look at some further questions then. So again, we've got another a question with working out. So it's told a teacher asked two students to solve the equation 2 cos x equals 3 sin x for minus 180 to positive 180. So here. Now we are not between 0 and 360. We are between minus 180 to positive 180. So we do need to keep that in mind. So we're told the attempts are shown below. So again, well, part C says write down the correct answers to the question. So we're going to need to solve it anyway. So let's try and solve it first, and then we'll see what each student's done differently and where they've gone wrong. So, we're going to solve this then. So again, we can't factor anything out, right? If I move the 3 sin x to the other side, say if I did 2 cos x minus 3 sin x equals 0, I couldn't factor anything out, so therefore I am free to then divide, right? To simplify the equation, I can then divide through. Well, what am I going to divide through? Well, again, we need to use our identities then, so we should recall that tan theta is the same as sine theta over cos theta. That hints I should divide by cos theta then, to both sides. So then I would get 2 cos x over cos x equals 3 sin x over cos x. Well, cos x over cos x cancels, so I'm going to get 2 equals 3. Now, sin x over cos x is indeed just tan of x. Well, there we are. So then I can say that tan x then, if I divide by 3 to both sides, is 2/3. And then I can proceed to solve from there. So if I do inverse tan then, I get the first solution of 33.69 blah 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 degrees. So then to find the other solutions, let's consider the tan graph. Now, we remember we are between minus 180 and positive 180. So, that's what we're going to work with. So, if we draw a tan graph, there we are. So, it'd be 90 there. And then 180 would be there, right? And then we need to go to negative 180 as well. So, if we continue the graph on, at minus 90 there, and there we are, and that would be 180, minus 180 there. Right, so the first solution is 33.69, right? So that would be about, say there, 33.7, right? It would be somewhere there, right? So then if we read off our graph, the other solution would be about there, right? But to get the other solution then, that's just 180 to the left, right? So that's, we have to subtract 180, right, to get to that point. So then that would be either or 33.69 take away 180. If I do that on the calculator, I get minus 146.309 blah 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 degrees, right? And so that means that point here, that point there would be minus 146, right? 0.3. And so there we are. So those are the two solutions then. Between minus 180 and positive 180. So there we are. So then let's round it. We would either have x is 33.7 or minus 146.3 degrees to one decimal place. And there we are. So those are the solutions between minus 180 and positive 180. So that's how we get, that's the solutions we get then. That's the solution to that equation. Now, let's have a look at the working then. So we've kind of done part C then, right? So part A, so the mistake in student A's working, let's kind of compare with our working then, right? So they got tan x is 3 over 2. Let's have a look. Oh, well, we got 2 over 3. We got the other way around. So that's the mistake then. So the student, the mistake with student A, mistake is they did tan x is 3 over 2. So that's wrong. So tan x is 3 over 2 instead of tan x is 2 over 3. Right. So they probably made like a silly error, right? But that's the mistake. It should be 2 over 3, not 3 over 2 there. Then, very similarly, they then want to spot the mistake in student B's working. Right. Now, this is quite interesting. And this raises a very good point. That's why I picked the question. Student B, what's the difference? Well, they've not really got anything to do with tan. What have they done? Let's have a look at the first line of working then to see what they did. So they started with 4 cos squared x is 9 sine squared. Well, the equation we have is 2 cos x is 3 sine x. What have they done? Hopefully you spot they've just squared both sides, right? 2 cos x squared is 4 cos squared x. And 3 sine x, that squared is 9 sine squared x. So they've squared both sides. Which actually raises alarm bells. Okay, so they did that then. It's not really the best approach, but you could do that. But then they factorized. No, they used the identity. Cos squared plus sine squared is 1. And because then they said cos squared is 1 minus sine squared. That's fine. If you rearranged it, that's what you get. And that's equal to 9 sine squared. That's correct. Then they said 4. So then they expanded the bracket and collected like terms. So 4 would equal 13 sine squared. Yep, that would be right. And then they said sine x. Well, if we did a bit of work in ourselves, if 4 equals 13 sine squared x, then sine squared x is 4 over 13. So then if you square root both sides, you get sine x is plus or minus root 4 over 13. So that's correct then. And there we are. So the error then is to do, with the squaring bit, right? In general, you should be very careful, again, if you're squaring, right? Because what's the problem with squaring? We did look at this when we did when we looked at quadratic equations. It's the same concept there, but in chapter 2, we looked at when when you square both sides, you introduce extra solutions, right? So the problem is then, if you're squaring both sides, so the student squared both sides of the equation. They squared both sides of the equation, which introduces or adds extra solutions. Remember, we call that extraneous solutions, right? Okay. Now, there's not anything inherently wrong with squaring both sides. But if I get rid of this tan graph now to make more room, but because when you square both sides of an equation, you often add extra solutions. What you then need to do is, if you are going to do that, you need to then check every individual solution to see, and then substitute it back into the original equation here. So those four values of x, you need to substitute each of those values of x to see if it's correct, right? To see if it does indeed satisfy the solution, because some of them won't. Now, if we compare that to our answer, we only got 33.7 and minus 446. But they have minus 33.7 and plus 146. So they got an extra two solutions there, which would be wrong, right? So they needed to check it, but they didn't. They just said, well, that's the solution, so that's it. What they should have done was checked it. So I would say, so they added extra solutions, which are wrong. So they needed to check them. Okay, and so yeah, so the issue was, well, when you're squaring both sides, then you then need to check every solution you get from that, right? There's nothing wrong if you want to square it, but you then need to check every solution, because some of them might be wrong because you added extra ones. Okay, so the student failed to check and substitute every single value of x back into the original equation to see if it truly is correct. So that's what you got to do then. If you want to square both sides of any equation, not just this one, you then need to substitute your answers you get from that back into the original equation. Right, so then we got this question then. So it says to find all values of theta to one decimal place in the interval between 0 and 360. Tan squared theta is 9. Now again, this means tan squared, so I'm the square of it, right? So actually, this question shows that there are some equations where we need to boil it down to multiple. So what I mean by that then, if this is tan squared is 9, this is like saying x squared is 9, right? Well, how would you solve x then? You'd have to plus or minus root 9, which is 3. So we're going to do the exact same concept here. So then tan theta is going to be plus or minus root 9, which is 3, okay? And so actually then we've got two different equations, so the multiple equations I'm talking about. So we can split this into either tan theta is 3 or tan theta is minus 3, and we'd get solutions from both of them, right? So we solved them separately. So we've got two different equations now, but you do them in the same way we've just been doing. So tan theta is 3. Firstly then, as always, we'll do inverse tan to get the first solution. So if we do inverse of 3, we'll get 71.565 blah 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 degrees, right? Now, then to find the other solutions, let's sketch the graph of tan. So remember again, we are between 0 and 360. Remember, always pay attention to the interval we've got. So let's sketch between 0 and 360. So here would be 90, the asymptote. Then we continue it on. Then we get 270 for the next one. And then at the end there we got 360. Now the first angle was 71.6, say, so that'd be around there, right? 71.6. Then if we read off the graph, the next solution will be 180 after it, right? Because it repeats every 180. So the other solution then would be, or theta is 180, add 71.565. And if I do that, I get 251.565 blah 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 degrees. So therefore then, those are the only two solutions between 0 and 360, as you can see on the graph. So therefore we either get theta is 71.6 or 251.6 degrees to one decimal place. Alright, so those are all the solutions arising from that equation. Then we need to look at minus 3 here. So again, we're going to do inverse tan of minus 3. And that would be minus 71.565. Okay, so then if we do our tan graph again, between 0 and 360, because that's the interval we're working in. There we are. Now, our angle is negative 71.6. So if we continue our graph on, and then we have minus 90, minus 71.6 would be about there, right? So then if we continue that on, right, we would get two more solutions, right? There and there, right? If we continue that that on. How do we get these other two solutions then that are marked? Well, we need the both, again, they're repeating, right? So the graphs are repeating in that way. So we need to add 180 on to get the other two solutions. So we're going to get, or theta is minus 71.565, add 180. 90. If we do that then, we get 108.43 blah 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 degrees, and that would correspond to that corresponds to that solution there, right? If we read that off, it would be 108 there, right? But then to get to this other point, this next point along, we need to add 180 onto this then, right? Because again, it's repeating every 180. So, or 108.43 add 180 gets me 288.43 blah 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 degrees. And actually it's these two solutions that are between 0 and 360, right? This 108 and this 288. Those two solutions, again, as you can see on the graph, are between 0 and 360. This negative 71 is outside the range because it's negative, it's below 0. So the only solutions we're interested in are 108.4 and 288.4 degrees to one decimal place. Yes, to one decimal place. So overall then, if we combine the two equations, our overall solution, so overall, the solution for theta is 71.6 degrees, 251.6 degrees, 108.4 degrees, and 288.4 degrees, right? So when you're solving multiple different equations, at the end you need to combine them together, right, to get one big list of answers. So there we are then, right? So when you might have instances then when you need to square root both sides, and then you split it up into plus and minus and solve from there, right? Okay, let's have a look at this question then. So we are told firstly to show that 4 sine squared x minus 3 cos squared x equals 2 can be written as 7 sine squared x is 5. Now, so this is going to be identities again, right? So if I recall them, there we are. Well, what I notice is the cos squared goes away. There's no cos squared in that equation, only sine. How can we... And I notice it's cos squared. Well, I can use this identity then, right, to get that cos squared, get rid of it. If I rearrange that, I therefore get that cos squared x is 1 minus sine squared x. And I can substitute that in then. So then I could say then that... then 4 sine squared x minus 3, now cos squared is this, so it's going to be 1 minus sine squared x equals 2. And that can be a common strategy, right? If you need to eliminate sine or cos, sine squared or cos squared, you can use that identity. Anyway, if we expand that then, we get 4 sine squared x minus 3, add 3 sine squared x equals 2, then 7 sine squared x. And then if we add 3 to the other side, I then get 2 add 3, which is 5. There we are. Cool. So there we are, that's part A done. So again, you do need to know your identities. They can come up. But there we are. Then we need to solve between 0 and 360. The equation 4 sine squared x minus 3 cos squared x is 2. Well, isn't that equation that we proved in part A to just be this, 7 sine squared x is 5. So solving that equation is equivalent to solving this equation we found. So we just solve that. So solve 7 sine squared x equals 5, right? Because them two equations are equivalent, right? Now, again, we need to solve for sine theta, or sine x. So let's get rid of this 7 firstly. Divide by 7. So sine squared x is 5 over 7. Right. Okay, so now we have sine squared x. So we need to square root both sides. So we get sine x is going to be plus or minus, right? When solving. If you square root both sides, you need to do plus or minus. Root 5 over 7. Right, okay. So that again leads me to two possible different equations to solve. So firstly, sine x is positive 5 over 7. Oh. And secondly, sine x is negative root 5 over 7. Right? Okay. So let's solve this one first. So firstly, if we then did inverse sine of root 5 over 7, I get 57.688 degrees. Okay. That's what I get from the calculator. So again, then I'm going to sketch my sine graph. And again, it's between 0 and 360, right? There we are. So 57.688, that's going to be about, there, say, 57.9. So then the other solution, if that's 360, the other solution in this range between 0 and 360, well, it's going to be, well, again, the gap between at one end at 0 and 57.9 is just 57.9. So then the gap between the other solution for x and 180 at the other end of the curve is also going to be the same, 57.9. Which means the other solution is going to come from taking away this 57 from 180, right, to get that other solution. Oh, 57.7, sorry. That was it round. Sorry, 57.7, not 9. There we are. So 57.688. If I do that on a calculator, I get 122.31 blah 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 degrees. So actually then those are the only two values we can see that are between 0 and 360. So overall then x is 57.7 degrees or 122.3 degrees to one decimal place. And there we are. Cool. Now let's solve this. So sine x is minus root 5 over 7. So if we did inverse sine, we get the first solution of minus 57.688. So if we sketch our graph again, our sine graph, so 360 is there, but our angle is negative 57, so we're going to need to go backwards a little bit, right? Right, so then minus 57 would be about there, right? So then if we read off our graph, we got two more solutions there and there, when it also cuts the graph, right? How are we going to work that out then? Well, the next solution there, the next solution after that, well, again, the gap, if we have 180 here, the gap between this solution for x and the gap between minus 57.7 and 0, right, that's going to be 57.7, right, the same gap. That gap is also going to be between 180 and this next solution, right? That gap is also going to be 57.7, right? That same gap between 180 and 57.7, which means then to get the other solution then is going to be adding this 57.688 to 180. If I do that on the calculator, I get 237.688 blah 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 degrees, right? So that means that this solution then, so it was there and there, right? So this solution will be 237, say. But then what about that solution? Well, hopefully this other solution, right, you can spot it's just 360 after this one that we found, this minus 57. It's 360 along, it's repeating. So all I need to do then to find that other solution is add 360 on. So minus 57.688, and then we're going to add 360 on. Alright. So if we do that, we get 302.31131 blah 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 degrees. So therefore then, the solutions between 0 and 360, so the positive part of the sine graph there, are these two other solutions we found here. So overall then, x is 237.7 or 302.3 degrees, right, to one decimal place. There we are then. So we got the two solutions then. So if we combine the two overall, so if you get the overall solutions then, we have x is 57.7 there, 222.3 or 237.7 or 302.3 there. Okay, and there we are. Cool. Those are all the solutions between 0 and 360. Cool. Yes, to one decimal place. Okay. Cool. Now, we're going to finish off with an exam question then, exam style question. So we firstly need to show this whole monstrosity is identical to 4 minus 5 cos theta. So this is just proving an identity. We looked at questions like this last time, if you need a recap. But the idea is that we're going to need to use these identities to help us, most likely. You need to have these in the back of your mind. So Again, with identities then, on one side of the identity, I then need to simplify it to get and end up with the other side, right? And I usually want to work with the more complicated side and break that down. Well, clearly this fraction is probably what we're going to be working with, right? So let's start with this. 10 sine squared theta minus 7 cos theta plus 2 over 3 plus 2 cos theta. Right, so where am I going to start? Well, have a sine squared here. I notice I can apply this identity here, right? So there we are. Let's try and substitute that in then. So obviously sine squared and cos squared is 1, therefore sine squared, it's going to be 1 take away cos squared then, right? If I substitute that in then, I get it's identical to 10 lots of 1 minus cos squared theta minus 7 cos theta plus 2 over 3 plus 2 cos theta. Cool. And if I expand that all out then, I get 10 minus 10 cos squared theta minus 7 cos theta plus 2 over 3 plus 2 cos theta. And I can collect the like terms, right, on the top. So I have minus 10 cos squared theta minus 7 cos theta, and then 10 add 2 is plus 12, right, over 3 plus 2 cos theta. Now, right, what can we do there? Hopefully at this point you can sort of realise we got a quadratic, right? A quadratic but with cos, right? Have a cos squared, a cos and a number at the end. This is a disguised or a hidden quadratic, which we actually also looked at in the quadratics chapter. So we can actually factorise this. Remember what you should always aim to do is try and factorise stuff with these identity questions. If I said that u is cos theta, then this numerator is minus 10u squared minus 7u add 12. We can factorise this, right? So if I factor let's factorise it then. But I'm gonna tell you a bit of a cheat code with this. Obviously, we know how to factorise quadratics. Hopefully, we've seen that. Obviously, you'd try and find two numbers at times to get minus 120 and add to get minus 7. And you can go from there. But there's a lot of factors with this minus 120. What we can do then instead, and we can actually use the factor theorem to help us, we can find the two roots, right? If I make this equal to 0, I can solve this equation. So u would then be plus 7 plus or minus a square root of minus 7 squared. Take away 4 lots of minus 10, lots of 12. Let me write that a bit neater. Oh. There we are. All over 2 lots of minus 10. If I put that in the calculator, I get u is 4 over 5, or u is minus 3 over 2. Okay. Right, now we can actually get rid of these fractions, right? Because if we were to factorise at this point, we would say u minus 4 over 5, u plus 3 over 2 equals 0, right? Now, with factors in brackets, I don't want fractions in it. So actually, we can get the proper factorisation. Well, actually, if u equals 4 over 5, if we times that by 5, I would get 5u minus 4 equals 0. Or 2u add 3 equals 0, right? Because then 2u would equal minus 3. Move that minus 3 to the other side. 2u add 3 equals 0. And these are my factors then. So then I can say 5u minus 4, 2u add 3 are my factors, right? of this quadratic here. However, to note, we have minus 10 here. If we expanded this out, we'd get 5u times 2u would be plus 10u. So what we need to do to account for that is just whack a negative on at the end there. Okay, and there we are. That is the proper factorisation, right? So we don't actually have to go through the process that we looked at last time. We can sort of use the factor theorem if we can find the roots to find the factorisation that way with nasty quadratics, right? So there we are then. Well, if we put that back in then, so we said that minus 10u squared minus 7u plus 12 is the same as this factorisation. So minus 5u minus 4, 2u add 3. But then we can put this u back in then. So therefore, we can say that the factorisation is, if it lets me, minus 10 cos squared theta minus 7 cos theta add 12 is the same as minus lots of 5 cos theta minus 4, 2 cos theta plus 3. Right, if I just put u is cos theta back in. Well, there we are then. So we've got a factorisation for this quadratic of cos. So if we substitute that in then, this is the same as minus of 5 cos theta minus 4 of 2 cos theta add 3 all over 3 add 2 cos theta. Well, hang on a minute. 2 cos theta add 3. These two are the same then. The top and the bottom factor there. You can cancel that out then. And we're left with just minus 5 cos theta minus 4. And if we expanded that out by times it by negative, we would get 4 minus 5 cos theta. Well, hang on. There we are. We got what we wanted, got to the other side. So there we are. We're showing that then. Cool. That's part A done. Then it says, hence or otherwise, solve between 0 and 360. The equation 10 sine squared. Okay, that same fraction, which is now equal to 4 plus 3 sine x. Right, now this is a very sort of common question, exam question. What you can do then, instead of trying to solve with that ugly fraction, we need to use part A. We can substitute that fraction is the same as this. So this is the same as saying 4 minus 5 cos theta is just 3 is equal to 4 plus 3 sine x, right? So we can just say that actually we can say that 4 minus 5 cos theta instead of the fraction of the big fraction is equal to this. So 4 plus 3 sine x. And again, we are between 0 and 360 degrees. That's what we're working in. So, how are we going to go solving it? Well, firstly, we can take away 4 to both sides, right? If I take away 4 to both sides, I just get minus 5 cos theta is 3 sine theta. Cos theta is 3 sine theta. At that point then, I can then divide by cos theta. And I can do that because I can't factor anything out. So therefore, I just divide. Well then, if I divide by cos theta, well, minus 5 cos theta over cos theta would be just minus 5. And that'd be equal to 3. Then sine theta divided by cos theta, again, remember that's tan theta. That's the identity, right? As tan theta is same as sine theta over cos theta, right? Okay. But then if we did just rearrange for just tan theta by divided by 3, we then get tan theta is minus 5 over 3. Okay, cool. Right. Well, then we need to solve that equation then, right? So again then, the first step we're going to do inverse tan to get the first solution from the calculator. If I do inverse tan of minus 5/3, I get minus 59.036 blah 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 degrees. Then to find the other solutions between 0 and 360, that's our tan graph. And then 360 is there. But we have a negative angle here of negative 59. So if we continue that graph on the other way, so that would be minus 90 there. So minus 59 would be about there, right? So then if we continue that graph on, if we continue that on, we get to that other solution and this other solution here as well, right? So to get to the other two solutions, well, again, they're just repeating. Every 180, I get the second and the third solution as well. So if I add 180 on then to this solution, I get the solution 120.963, sorry, blah 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 degrees. So that would correspond to that solution there, right? 120.9, right? Now to get the other solution there, the solution after it, well, it's repeating again, right? The graph's repeating again. So I need to get another 180 to this. If I do that then, this solution added 180, get the next solution 300.963 blah 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 degrees. And that's all the solutions then between 0 and 360. Now then, so with that in mind then, the solutions between 0 and 360, well, it's going to be, if we look at our list of solutions then, between 59, minus 59, 120 and 300, the solutions between 0 and 360. So so between 0, no, it's x, we're solving for x, weren't it? But so I should probably change that to an x. They're usually not that pedantic if you use the wrong lettered variable, but it's best to be a bit safe. So between x and 360, so between 0 and 360 degrees, the solutions that are in that range is 120.963. Now what do we need to round to? It doesn't tell me what to round to, so let's just round it to, let's say 2 decimal places, 120.96 degrees and 300.96 degrees to 2 decimal places. And there we are. So those are my solutions to that equation then. So there we are then. So that's we looked at that's solving trig equations. So that's the whole idea, right? We can use the cast method if we want to, but I think it's a lot better to use the graphs, right, to work out the solutions by looking at the symmetry or the patterns of the graph, right? And so yeah, so that's the procedure. And so yeah, we will be looking at harder equations in the later on in the chapter and in year 2 in maths, but it all boils down to solving equations like this. So you must be very confident with being able to solve the equations we looked at in this video. Okay, but yes, that's it. I'll see you next time.